here with us. So hi everyone, welcome on board. It's really good to see that so many of you are here with us today. Hope you are all well. This is the second online event in June organized by the Hungarian NLP meetup. We wish to thank Crown Intelligence for its financial support with which this webinar could be realized. And we are also really grateful for the Bay Area NLP meetup, London Text Analytics meetup, and NLP NY for advertising this event. And last but not least, we appreciate Manning's help with which we could meet with Robert. Let me introduce myself. I'm Orsolya Puc, one of the organizers of the Hungarian NLP meetup and your host today. Actually, I'm a cognitive linguist and work as a researcher at Crown Intelligence, which is a boutique consultancy specialized for NLP and data science. But so much about myself, and now let's turn to the topic. Today, Robert Munro presents his ideas about active learning for NLP. Robert has worked as a leader at several Silicon Valley machine learning companies and also led AWS first natural language processing and machine translation solutions. Robert is the author of the excellent book, Humanintheloop Machine Learning. He organizes Bay Area NLP, the world's largest community of language technology professionals. Robert, as he has already told us, is also a disaster responder and is currently helping with the response to COVID-19. Before giving the floor to Robert, let's see some practical details of this event. The presentation was pre-recorded and it lasts for 40 minutes. During the talk, you can raise questions via chat and Robert will answer them real time. In the end, we will also have 15 minutes for more questions. And Robert, if you are ready, then I wish to ask you to start your presentation.
Hey everyone, welcome to my presentation on active learning for natural language processing. My name is Robert Munro and I run the Bay Area NLP meetup group, but I'm here today hosted by the Hungarian NLP meetup group. And I know we've got a lot of other people from communities around the world joining us too. I'm aware of people in Australia, New Zealand, Japan, Malaysia, South Africa, all across Europe and all across North and South America joining us today. So I'm glad that you're able to take part today, no matter what time of day or even day of the week that you're joining us. And for the presentation itself, I've actually pre-recorded this component. So what that means, if you're watching us live on Zoom right now, not watching later on YouTube, if you're watching live on Zoom, I can take your questions as we go. They should be able to see me in the Zoom chat if you would like to bring that up. So I'm happy to take your questions via text on the Zoom chat as this presentation goes. And then we're also going to have time at the end. So at the end of the presentation, I'll be able to answer some of your questions live. Thanks to our hosts there. And so no matter what your background is, whether it's in natural language processing, whether you're an engineer who's interested in natural language processing, or if you're in an adjacent field like information retrieval or speech recognition or machine translation, I hope that there is going to be something interesting for you in this talk today. So the talk I'm giving is an excerpt from my book, Humanintheloop Machine Learning. And it's answering what I think is one of the most important questions in technology today. How can humans and machines work together to solve problems? And so those of you who work in machine learning know about 90% of machine learning applications improve with human feedback. They typically use supervised learning or something really closely related like lightly supervised learning. And human feedback can help machines understand confusing or new data. And this applies to a whole range of different use cases. So whether it's commands spoken that are sent to your smart devices, videos from the front of autonomous vehicles, or information extraction from healthcare-related messages. All these cases that I've worked on recently additional human feedback increases the accuracy. So a typical human-in-the-loop feedback system could look something like this. You have a deployed machine learning model. You employ active learning, the main topic of this talk, to look at the most interesting items for human to review. Humans review those items. They create the annotations on those items, which creates the training data, and then you can create your machine learning model to be redeployed. You can also use transfer learning, and transfer learning is the process of taking existing models and adapting it to your case, to kickstart or to augment your machine learning algorithm. The focus on this talk, active learning, is important when you have a very large number of unlabeled data items, and you might not have the capacity to employ people to manually annotate all of those items. So this comes from part 2 of my book, where I talk about different active learning methods, uncertainty sampling, diversity sampling, and advanced methods. I'll go through all of these in the presentation today. These chapters are already out, and then I'll give a sneak preview of a couple of topics from chapters 9 and 10, which are the next 2 chapters that I'll be publishing in the book, about advanced quality control and transfer learning methods that are very cutting edge and related to some of the interesting, more recent advances in active learning. So why would you use active learning? Accuracy is often cited as the main one. So let's say you have budget to annotate 1% of your unlabeled data. You want to make sure that it's the most important 1%. Speed is often another important factor. You want your model to be more accurate more quickly. And this has often been the primary use case for myself when I've used active learning in disaster response situations. I want to be able to translate or filter or extract information from messages following a disaster, sometimes in languages for which we have no existing annotations. And so being able to get a model up quickly and iterate on that is something that can help save lives. And so in that case, it's less about the amount of human input, more about the speed of getting a good model out as quickly as possible with all the data that we can feasibly annotate. And then finally, diversity. So unless you're looking at academic data sets, a random sample of unlabeled data is typically biased. The unlabeled data that you have available to you, your raw data, would typically be oversampling from some data source. And a lot of the time, that data source may be itself overrepresenting more privileged people. In natural language processing, the most obvious use case is when you have large amounts of text data, English will tend to be overrepresented. English only makes up about 5% of the world's conversations daily, but it makes up a much larger percent of almost all text data sets which are out there. And so selecting through different languages is fairly easy with language identification. We can have more subtle but equally problematic ways that your data might be biased. So before I start, I'd like to debunk 3 active learning myths, which are very pervasive. One is that active learning and random sampling converge with enough data. And so this is only true on academic data sets where active learning is simulated. The argument here being that you don't need active learning if you have enough budget, because once you've annotated, say a few 100,000 items, your model is going to be just as accurate from random sampling as it was from using active learning. This simply isn't the true unless you only started with 100,000 items. Unfortunately, academic data sets are randomly sampled. So maybe an academic data set has 100,000 items, which were randomly sampled from a pool of 1 million items that you no longer have access to or the ability to create labels for. So if you look at a lot of academic papers which are simulating active learning, it can mislead you as to the effectiveness of active learning. Another is that uncertainty is tractable and can be read directly from softmax. So I've seen people as prominent as Jan LeCun claiming this recently, and this simply isn't the case. So if you have a binary classification task, you can read the confidence directly from your softmax output, but anything more complicated than a simple binary classification task means that there are multiple different ways of calculating uncertainty. And no one way is guaranteed to be the most optimal way for your data. And calculating the optimal uncertainty for anything beyond a binary task is an optimization task in its own right. In fact, a lot of the advanced uncertainty sampling methods are themselves machine learning algorithms. Finally, related to uncertainty, one of the myths is that softmax base of E, Euler's number, is a special case of that number. And that simply isn't the case. In fact, if you converge your model with a different softmax value, you'll get the same model optimization. And so this isn't a case where Euler's number is special. And while changing the base, or equivalently the temperature of your softmax output, won't change what is the most confidently predicted item, and therefore won't change your accuracy, it can in fact change the rank ordering of items. So what is the most uncertain item from your pool from one base, or equivalently temperature from softmax, will be different if you change that. And you'll find this myth perpetuated out there. This is a special case for Euler's number when it is not. And you'll also find that almost all of the active learning literature ignores this as an additional parameter that needs to be looked at. So while the second two of these myths here do make active learning a more complicated problem than many people assume going in, it also makes it a more interesting problem as well. It's a new area where we can look at models. These models are inherently looking at the interaction between machine learning uncertainty and human understanding. And so any time spent working on these kinds of problems teaches us a lot about how humans and machines can solve problems together. Before I jump into the methods themselves, I want to give an idea of how popular active learning and human-in-the-loop processing is right now. So I'm going to go through 10 examples here and the benefits that come from using human-in-the-loop machine learning. So avoiding bias. AI will have biases which are different to human biases, and so having a human in the loop of decision making is one way to avoid biases in both humans or AI. It's also a way to create employment. So by some measures, the majority of people working in machine learning are creating training data. Actually, more people labeling data than creating algorithms for artificial intelligence. And when done properly, creating employment for human labeling can become a great way of bringing people into the information economy who previously wouldn't have been able to work in the information economy. And again, when done properly, quality controls can be a lot more egalitarian. So the demographics of a person should not necessarily affect the quality of their task, meaning that it's more of a meritocracy in terms of being rewarded for your work. Human-in-the-loop processing is also important for augmenting rare data. So in this example at Facebook, looking at misinformation, you can imagine that for very rare languages, there isn't even enough unlabeled examples to build training data sets. Certainly not enough to get to the same level of accuracy as for a language as English. And so having a human in the loop can augment rare data and is another way of avoiding bias. In this case, bias towards the amount of available training data. Human-in-the-loop processing is also a great way to maintain high precision. It's a really good example of autonomous vehicles, in this case helicopters. So you certainly don't want a helicopter to ever fall below human level accuracy. And there are interesting UX implications about what's the right way for a machine to back off to a human and tell the human that needs to take over. Similar to pilots and helicopters, human-in-the-loop machine learning can be used to incorporate subject matter experts. So in this particular example here, it's experts in looking at surveillance of potentially illegal behavior in markets, and human-in-the-loop machine learning enables these experts to create training data in ways that would not be available to non-experts and keep them employed in this process. Similar to this, in auditing use cases, you need consistency and accuracy. This might be court audit. And so while you do need machine learning to scale, you also need to ensure that you maintain human level consistency and accuracy. And related to this again, human-in-the-loop processes can make work easier. So in this example of cybersecurity, it's automating some of the tasks that a security analyst is able to work in, but not necessarily all of them. And related to making an expert more efficient, but not necessarily replacing them, in a lot of medical use cases, we're seeing doctors and other healthcare professionals use machine learning as part of their decision process, but not being replaced by it. Finally, you can use human-in-the-loop machine learning to provide transparent accountability and increase safety. So in this particular example for visa applicants, the system backs off to a human only in the negative case. So if an automated system rejects someone's visa, that's double checked by a human. So this is a use case where some of the outputs they're happy for or willing to accept some false positives going through. So maybe people getting visas that shouldn't have. But for the negative use cases, they're not going to allow those to necessarily affect someone's life without further human review. And finally, is kind of a fun use case where Formula One is testing changes to the rules using people playing esports, using gamers to test out those change rules and look at the safety implications there. And so all of these use cases you just looked at were reported within 1 month of each other. So hopefully this gives you a really good idea of how widely adopted human-in-the-loop machine learning is right now. Certainly we hear about a lot of different kinds of advances in AI and in NLP in particular, with a lot of really fun advances recently in pre-trained models. But certainly there are no recent advances that you can point to that are being so clearly adopted across so many industries in the real world. And obviously, something that's really missing is a lot of information about how to implement these different methods. Not many people get taught about active learning or human annotation in their undergraduate courses. And I think this is a real gap that I'm trying to fill with my book. So one way that you can think about these different methods is in a knowledge quadrant, where your known knowns, your known unknowns, your unknown knowns, and your unknown unknowns. And so to go through all of these in turn, your known knowns are your current model. It's confident predictions. So anything your model is confidently predicting and getting correct, these are what your model knows that it knows. Your known unknowns is what your model knows that it doesn't know. So if you have a binary classification task, these are everything that are around 50% confident, everything right at the decision boundary. So your model knows that it's uncertain in these particular cases, and this is where we use uncertainty sampling. One of the types of active learning that we'll talk about today. Uncertainty sampling targets items near the decision boundary. Your unknown unknowns, needless to say, are harder to identify. So how do you know when you don't know something? These are gaps in your current model knowledge. And the set of methods for trying to work out what you don't know that you don't know are known as diversity sampling. And we'll go through some examples of these in today's talk as well. And we're only going to touch on it briefly, but to round out the quadrant, transfer learning are your unknown knowns. So what latent information is there in related machine learning models they don't know is there yet, but if you adapt to your current problem, might be useful for increasing your model's accuracy. So to begin with, we're going to look at uncertainty sampling. So when your model is confused and you want to sample those items because those are the most likely to be predicted incorrectly, because the closer the decision boundary, the most likely to move that decision boundary if they are currently incorrect. So here's an example of a simple binary task. We have label A and label B. And uncertainty sampling should ideally target these 5 items with the question marks in the middle of them. So these have been selected to label because these are the 5 closest to the decision boundary. So active learning, you might apply your model to millions and millions of unlabeled items, and then you're selecting those which are, in this case, the most uncertain. And for our worked example, let's assume that we have a 4-class prediction task, shown here on the left, which could be expressed as a PyTorch tensor here on the right. So we've predicted y0, y1, y2, and y3, and the most confident item is 64.39% with our 4 labels. And we can build on this typical output from softmax, known as a probability distribution, and to look at different kinds of uncertainty sampling. Just to flag, the outputs of softmax are not strictly probabilities, but when you have outputs that sum to 1, this is known mathematically as a probability distribution. I go into more detail about the pros and cons of softmax in my book, but I won't go into more detail in the talk here today. So the most commonly used uncertainty sampling method, and probably one that you have used in the past, is least confidence sampling. And so this is simply looking at the difference between the most confident prediction and complete confidence, 100% confidence. So here our most confident prediction is 64% confident, and we are able to take that and know that because there's 4 items, it couldn't be less than 25% confident. That's the minimum. So here we just have that denominator as a normalizing function to give us a 0 to 1 range, where 1 is the most uncertain. And all of our methods will be in a 0 to 1 range. So this is something I highly recommend. Otherwise, you will get different ranges from different uncertainty sampling methods, and in some 1 will be more uncertain, and in others 0 will be more uncertain. And if you don't remember to normalize them, you're going to get into a lot of trouble in downstream processing. And also depending on the type of method you're using, some downstream processors will assume a 0 to 1 range. So margin of confidence is the difference between the top 2 most confident predictions. So this is also something you might have used in the past. So here the most confident prediction is 64%, the next most is 23%. So we're looking at the difference between them, and again normalizing for the maximum possible difference. Related to margin of confidence, ratio of confidence looks at the ratio between the top 2 most confident predictions rather than the difference. And we don't need to normalize this because the smaller of the 2 divided by the larger of the 2 is already in a 0 to 1 range. This is actually more mathematically well motivated than taking the difference. It's more mathematically well motivated to take ratio, but it's rarer in the academic literature. And this is mainly because the methods predate the current types of machine learning algorithms that we're using. But even though ratio of confidence is rarer, this should actually give you a more accurate indication of the difference between the top 2 most confident items. Finally, entropy uses information theory to look at all of the predictions. So in this case, it's looking at the difference between all of these predictions and predictions with no information, which would be the case that they were all 25% confident. And so entropy takes into account all of the predictions, not just the top 2 or the top 1, like you saw with least confidence predictions. And so any of these 4 methods might be the most appropriate one to use with your data, and you don't know without testing. So you should try out these different methods if you're using active learning and see what's right for your data. To get an intuition for what these different methods do, you can play around with it, and I'll share this link in the chat as well at my website here. So if you go to that site, you can click and make your own labels. Here in the top left, we can assume that we have 3 labels. These are the 3 black dots. And here are how these 4 different methods for uncertainty sampling pattern. So you can see that the 2 that look at pairwise confusion, margin of confidence, and ratio of confidence, we have these long bands coming out where pairwise confusion is enough. You can sample the uncertain items there, the most red items. Whereas entropy, which looks at confusion across all of the items, it concentrates where it samples right in the middle of those 3. At least confidence falls somewhere in between. You kind of get a secondary effect of looking only at the most confident, that it effectively also takes into account the other items as well. And if you look at the right-hand side in the 4 examples here, you can see that with a large number of labels and a relatively random pattern, the area of items that will get sampled as being the most uncertain are very, very different. And so it's really important to think about what are the right methods that might be right for your data, to get an intuition for what kind of confusion is most important to you. Is pairwise the most important? Is it confusion across all your labels? And that can often be the best starting point for deciding which of these heuristics is the best one to begin with for uncertainty sampling. And then you can think about trying the other methods and also building out some of the more complicated uncertainty sampling algorithms on top of them that we'll be looking at later. There's also some interesting more recent techniques using Monte Carlo dropouts. And so you've probably done this in training your models before, randomly dropped out certain neurons during the training process so as not to overfit your model, applying the same technique at prediction time and then get in multiple predictions across the models with different dropouts, sometimes known as Bayesian deep learning. And it's called that because if you squint at the range of predictions that you get, it'll look like a normal distribution or a Gaussian distribution. That's somewhat pretentiously called Bayesian deep learning. It's certainly like a great method to use if, for example, you don't get reliable confidence estimates for your predictions because of the type of architecture you're using. And you can look at variation in terms of the actual model outputs, the logits, or even just the labels themselves, if that's what you have access to. So look at the items which are the most variable in the labels. And this builds on a long history of using ensemble methods, which is sometimes called uncertainty by committee in active learning literature. So that's uncertainty sampling. We're now going to move on to diversity sampling. So diversity sampling is trying to find what you don't know that you don't yet know. So these are gaps in your model knowledge. And the hard thing is obviously you don't know in advance what you don't know. So to go back to our example of the binary classification task, diversity sampling is looking to sample items that are very different from what has been labeled before, and also different from each other. So here are 5 items that have been sampled to be labeled through diversity sampling. And you can see, at least in this data set, they're the furthest from what's been labeled so far and they're different from each other. So sticking with our models, one way to look for outliers are things which have low activation in your models, low activation of logits and the hidden layers. So one of the problems with softmax is that it hides the scale of the inputs. So for example, if you have inputs of 1, 2, 3, and 4, the softmax distribution is going to be exactly the same as if those inputs were 1001, 1002, 1003, 1004. And so you don't know what might be confusing to your model because of conflicted information versus no information at all. And so looking at the average rate of activation across your model is one way of finding something that your model simply hasn't seen before. And then this is evidence that it might be something new or previously unencountered, certainly something that doesn't appear very often in your training data, at least not in a way that it resulted in your model being able to find much information from it. And you can experiment with which kinds of layers you want to look at. Obviously, if it's earlier layers, it's closer to your data. If it's later layers, it's closer to your prediction space. That can be more interesting, but then more likely to be biased towards your current model. Cluster-based sampling is probably the most common method of diversity sampling. And so that is simply clustering your data and selecting from each cluster equally. Representative sampling, you can think of as a variation on clustering. So you can think of it as creating one cluster that contains all your current training data and a second cluster that contains all the data that doesn't currently have a label. And so then you can look at what item looks most like your unlabeled relative to your current training data. So what do you not currently have a label for that looks like other things you don't have a label for? And so especially if you're looking at domain adaptation, this can be a really effective method of quickly identifying the most promising looking items from your unlabeled data in the domain that you're trying to adapt to. Final example is real-world diversity, so increasing fairness with data supporting real-world diversity. This could be demographics relating to people, like gender or ethnicity or languages spoken, or other demographics that you care about in the real world for your data, like maybe time of day, day of week, or other kinds of metadata. And so structured for real-world diversity means looking at, again, distribution relative to your current training data. In this case, knowing that you have other demographic information about your data, looking to see whether your data is representative or not. Something to remember here is that this will depend on your model architecture too. In some models, your data will need to be representative, otherwise biases will be perpetuated. In other cases, you only need a minimum amount of data to avoid biases. So most methods for successful active learning combine the two. Uncertainty sampling alone will tend to pick items that look too much like each other, and diversity sampling alone will pick items too far from the decision boundary. So ideally, you want a combination of diversity sampling and uncertainty sampling that'll sample items like these 5 here. These 5 are all close to the current decision boundary, but they're also far from each other. And I give a dozen or so examples of this in my book. I'll go through just 2 of them here to get an idea of how to combine them. Most of the ways for combining them are fairly simple. You'll play one method and then you play another immediately following. And this is one of those, uncertainty sampling and clustering. So initially, we'll apply uncertainty sampling and sample, in this case, something like just the 50% of unlabeled items which happen to be closest to the decision boundary, discarding the 50% which are further from the decision boundary. Then with those closest to the decision boundary, we'll apply clustering and then sample items equally from within each cluster. So obviously that cluster in the middle would have got way more if we're just randomly sampling, and we want diversity as well as uncertainty. So here we're getting that nice distribution of items near the decision boundary but distant from each other. And this is a really simple but powerful method. Unfortunately, you won't see it much in the literature because most academic papers only look at individual methods in isolation and then compare them for their relative value. And also, it's not probably worthy of an academic paper for the 2 lines of code to pipe your sample out of one method and into another. And that's fair enough for an academic paper, but certainly for practical active learning, it's worth looking at some of these simple combinations. And you'll find that in addition to a number of these being in the book, these are also in the open source code that's released with the book using Python, using PyTorch for the machine learning components. One of the more advanced and interesting recent techniques for combining uncertainty sampling and diversity sampling is active transfer learning for adaptive sampling, or ATLAS for short. So I'm sure you're familiar with transfer learning already. You have a model that is trained on one task, in this case predicting A, B, C, and D. You have some data, maybe only a small amount of data, labeled for W, X, Y, and Z, or Z, depending on where you're joining us from. And then you can train maybe just one new output layer to predict these new labels. And the advantage here is that you essentially get the representations from a potentially bigger data set for A, B, C, and D for your W, X, Y, and Z data set. So what's nice about transfer learning is that it doesn't matter what these other labels are. So these other labels can be something that you derive from the data itself. So let's imagine that you have held out validation data also labeled A, B, C, and D. So we care just about the A, B, C, and D task here. We can put that validation data through our model and then bucket everything into correct and incorrect. So let's say that we got half of our validation data correct, half of it incorrect. We can now create a new output layer to predict correct or incorrect. So it's a binary classification task that's trained on our validation data. And for any new unlabeled items, it is now essentially a classifier telling us with what confidence we can expect all our unlabeled data to be either correct or incorrect. Then we can find whatever is the most highest confidence of being incorrect, and we can know that, well, this is something that we want a human to review. Now, if we think our model is getting it wrong, we want a human to validate that. We want to update our training data accordingly. And then that's one of the most likely items for us to be able to increase the accuracy of our model going forward. What's nice about this kind of process is that because we don't know what the actual label is yet, but we don't care about it, we can make this adaptive before we even get that human feedback. So we know that once our model has seen this item, the incorrect item gets a human label, we know that that item and items which are similar to it are going to be labeled correctly because our model is now trained on that particular item. So we can make this assumption that no matter what the label is, we don't know what it is yet, but we do know that it will be labeled correctly, and were that added to the validation data, it will almost certainly be correct again, correct if predicted again later. We can then switch to the other bucket. We can now give it the correct label, and retrain our model with this now in the correct bucket. And this will give us the diversity component. So we'll focus initially on the area that has the most incorrect items, most confidently incorrect items. But once we have maybe just a handful of those, which we know that we will later get correct, and then retrain our model accordingly, then it'll start to sample items from other parts of the uncertainty space. So this is a nice way of combining uncertainty sampling and diversity sampling into a single algorithm. And certainly you can have more complicated transfer learning models with more new layers or using different layers into the output layer. But you probably only have a little bit of validation data, and having just a single binary task for your new output layer means you can probably get away without much hyperparameter tuning. And so again, if you look at the example open source code, there's implementations of active transfer learning for adaptive sampling that retrains a new output binary layer like this on the validation data and adaptively samples. In that particular use case, you'll see that we're looking at disaster response, a related example. And so looking at the text should also give you an intuition for the kind of things that get sampled. So finally, just a quick sneak preview into some content from upcoming chapters related to transfer learning. So again, similar to this method of transfer learning, can we take the output from one model and use it in another? In this case, rather than retraining a model for a new task, we're using one model as a representation in newer models. So this is what I'm sure you've done with things like embeddings before. What's interesting here, though, is that you might have some tasks which are much, much faster than others. So let's say you want to label A and B, but it's a very complicated task. You require subject matter experts. It takes them a long time to make a decision about label A versus label B. Maybe some sort of complicated medical diagnosis or financial analysis. However, you have an adjacent task, which you know that you can give to crowdsourced workers, and they can do it really high speed. And so while it's not the task you're looking for, it's closely related to it, and maybe you can do that 100 times faster or cheaper, and then use that as a representation. And so there's a really interesting paper here called Intermediate Training, and it's called Intermediate Task Training because they actually begin with a pre-trained model. And then they use like the YZ model here as intermediate one, and then AB for the output layer. And this really interesting, currently under review work shows that even when they are looking at tasks outside of English, as their AB task in this case, they can do intermediate training on a multilingual model just in English on a semantically related task, and it actually improves the output from non-English tasks. So it doesn't have to be too adjacent to get some accuracies here. In their particular paper, they're just looking at existing academic data sets. But this has some really interesting implications for active learning and annotation as well. You might change your entire strategy in order to get high volume of adjacent and easier to get labels rather than what your target task is. And then you can apply all of the uncertainty sampling and diversity sampling techniques to this model as well. In fact, to both of the models. You might want to look at some active learning within the YZ model in addition to the AB model. And I think we're really just scratching the surface of the possibilities here for the kinds of use cases that we can use for transfer learning and active learning. So it's an exciting new area. So some general advice. Build a system, then refine it. So chapter 2 of my book is a working human-in-the-loop machine learning system with 500 lines of code. There's some basic uncertainty sampling, some basic diversity sampling, a basic annotation interface, and a model that automatically retrains itself every period of active learning. And so doing this, taking it into the second point here, let you look at your data. So you're annotating your data quickly itself. That'll give you an intuition about what's going through and what the best algorithm might be. And then with your working very simple system, you should also get an intuition about what is the next best step to improve the accuracy. Is it improving the model? Is it improving the annotation interface? Is it improving the active learning methods to sample the right data? It may be that you're already close enough to optimal in one or more, of the components of a working human-in-the-loop system. And so rather than try and build state-of-the-art systems for every component of a complicated human-in-the-loop system from scratch, you can start with something simple and build on it from there. Finally, I'd advise to be realistic about time to reach accuracy. It's really hard in advance to predict what level of accuracy you're going to have from your model downstream. So if you can think of a way to productize your human-in-the-loop system that provides value from the get-go, then you're going to be in a position for success. So with that, I'm happy to take any questions now. I can take these directly in the Zoom chat for those watching live. If you're interested in a copy of my book, you can get 50% off here with the code TSLOOP at bit.ly/Hummel_book. Or if you just go to menin.com and look for Human-in-the-Loop machine learning, you should find it there. All right, well, thanks everyone. I appreciate you coming to this presentation, and I look forward to your questions.
Thank you, Robert, for this wonderful talk. I think it was amazing. We learned a lot. And as I have mentioned, we have 10 or 15 minutes for more questions. So anyone can write any questions, and Robert is still here to answer. Okay.
Oh, here we go. There's questions in there about where to order the book. I'm going to drop that back in the chat itself, so that you've got that there. It's not yet on Amazon. It's on my publisher's website. We've published 8 of the 12 chapters so far, and we will publish the rest when the other chapters are out, including hard copies, and it'll be available on Amazon at that time. But right now, the book is a lot cheaper to purchase online in advance, and I want as many people as possible to read this as cheaply as possible. So, so this is a good opportunity to get a discount.
Okay, there are some other questions in the Q&A section. Can you read them, or should I read them out? Like, for active learning in NER, what techniques do you recommend? Have you tried doing NER with character level models?
Yeah, so that's a great question. I've done a lot of named entity recognition in my past. It was part of my PhD. And we released the named entity recognition models at Amazon Web Services when I ran product for NLP there. Firstly, if you're looking at NLP, especially if you have character level or byte level encoding, you probably want to think about whether or not you want to calculate uncertainty over the entire span rather than the individual span. So in similar ways, in that the accuracy of your model is typically calculated by most benchmarks over the full entity, not over tokens. You want to aggregate the average uncertainty over a token as a whole. In terms of active learning techniques, some of the best techniques for active learning tie into human interfaces for a named entity recognition. So it is really slow to annotate, say a raw piece of text, maybe a news article for every location in that article. There's not very many locations. You're asking people to read a lot before they get to each location to potentially underline it. So one of the nice things that you can do with active learning is discover candidate entities, especially ones that might be confusing or novel through uncertainty sampling and diversity sampling, and then put this in front of humans and say, is this an entity, yes or no? And then have a more complicated workflow to know. And what's nice about that is you'll often get a 10x speed up at least for a human simply saying yes, no, is this correct, versus annotated raw data. You do have to be careful that you're not biasing your human annotators. To repeat caveat, this is by far the most efficient way to create named entity data sets. And it's certainly something I've done, creating named entity data sets for Amazon. I've created data sets for Google and IBM doing this as well. And it's always this human in the loop process where you're generating candidates for human review.
Okay, thank you. Can you say this other question? What is your recommendation if you have a good amount of fully labeled examples? So what can one do in this?
Oh yeah, I love this one. This is a great question from Robert Dumbleton here. There's two different approaches that you can take if you have poorly labeled examples. One is to try and identify poorly labeled examples. You can do this by bootstrapping. Cross-validating your model, training on 90%, predicting on 10%, looking where your predictions differ from the existing labels, and then those are candidates for human review. And so this is kind of like the classic way of taking poorly labeled data, looking for model disagreement and treating those as potentially mislabeled items. There are some more recent interesting techniques which are like the transfer learning example that I had here. So if you have a large amount of labeled examples which you don't trust, you can build a model on those badly labeled examples. You don't necessarily trust that model. So assuming that there's a subset of labels that you do trust, maybe they're labeled by experts or you're able to get better quality control in place, you build the model on those trusted labels, and then you use the potentially noisy model as a representation, as like an embedding in your actual model. And that allows your actual model to trust or not trust that noisy model at the right locations. So those are the two methods available to you, and I cover both of those in my book too.
Okay, it seems to me that there are no other questions, or we can wait, I don't know, 2 more seconds.
All right, we've got a few more minutes here. It looks like. Oh wow, it's a huge question there.
Oh yes. Okay. It's really
Oh, it looks like Robert Midmore is sharing another example there of a method I didn't cover. You probably don't want me to watch this live. Yeah, certainly there are many methods for active learning. I think I cover a couple of dozen in my book, and a few in the presentation today. Offhand, I'm not sure if this is one that I covered or not. I certainly, definitely recommend, if you're interested in this topic, looking at a lot of the innovative work out there. Also, I know it's not fashionable to look back in time before neural networks became popular, but there was some really innovative work, especially with support vector machines in early active learning in the 90s and 2000s. I see a lot of these being reinvented recently by people maybe not aware that they already exist. So if you are interested, I do recommend looking a long way back in the literature.
Okay, now some other questions arrived to the Q&A section. Like, is it more applicable? I don't know what
Computer vision or NLP?
What does easy?
Active learning is equally applicable to computer vision and natural language processing. It'll vary a lot depending on the task. So I didn't cover any of it here today, but one of the chapters in my book specifically talks about active learning for different use cases. In natural language processing, talking about document level labels, like I did in all the examples today, sequence labeling, like natural language processing, and then text generation, like machine translation or question answering. And then within computer vision, I talk about image level labeling, object recognition, and semantic segmentation. So a lot of the same general principles apply in terms of looking for uncertainty and looking for diversity, but there'll be different sets of methods. And as to what's more or less effective, it'll be less about whether it's computer vision versus natural language processing, more about whether your specific task has problems with initial data bias, whether uncertainty sampling is effective, which method is effective. And that can really just be more data dependent rather than the specific use case or type of data.
Okay, and probably the last question for today is the following. Are there any recommendations for retraining, as in which models to use, as retraining big models will be very expensive in live models?
Yeah, so I recommend starting with really simple models. Along with my book, I've released an open source library with all these methods and quite a few more. I wrote that in PyTorch. That doesn't necessarily mean that PyTorch is better than TensorFlow or other libraries. I really did that because I was already familiar with TensorFlow and I wanted to teach myself PyTorch or write in the book. Like I show there, especially when you have a small amount of data, you don't really want a big and complicated model to begin with. I think I have 128 neurons in one hidden layer in the example data. And then you can build more complicated models as you go. And that's something you'll have to think about in terms of strategy, the trade-off between model accuracy and your ability to retrain part or all of your model with your updated data. But certainly, I do recommend keeping it very simple to begin with, and then working out what you need to build on. Because it may be that a more complicated model only gets you a few percent accuracy. You might get tens of % increase with just a little bit more labeled data. And so that's something you'll need to weigh up.
Okay, and this is absolutely the last question because of the interruption. I think we can still have this one. What's the gap between the methods you go over and the snorkel?
So what was that? I missed that question.
So what's the gap between the methods you went over and snorkel?
Oh, snorkel. Yeah, rule-based methods. Actually, we have someone in the presentation today who's an expert on this, Abraham, who was asking questions earlier. I've seen him give a presentation about Humanintheloop machine learning with snorkel, which is really interesting. So rule-based methods, of which snorkel is one of the most sophisticated, are really good for ramping up quickly, especially if you have subject matter experts. But it quickly becomes unmanageable if you have a large amount of rules, both in terms of humans trying to get their head around it and the increase in accuracy and runtime as well. Runtime can actually be more expensive than getting model predictions. And so I do talk about rule-based methods in a later chapter and where they fit in next to machine learning. I would think of rule-based methods as something that you can use to generate potential label data quickly, maybe to use alongside other labeling techniques. But for sophisticated tasks of more than a handful of labels, I don't know of anyone using snorkel by itself for deployed machine learning systems.
Okay, so thank you again for this wonderful talk and also for your answers. I think it was a really fascinating hour which we spent together. So if you want to listen to similar talks, please check out our upcoming events on our website, on the website of the Hungarian Natural Language Processing Meetup. And that was it for today. Thank you, everyone, and I hope we will meet soon. Bye-bye.
Thank you all. We'll post the slides in video. See you later.
Thank you. Bye.